as I promised last time, today we will look at some of the examples solved using the equations that we derived in the last class, and that will be done by my students, Smriti and Prakhar. They are working with me as a PhD student. Okay, so you can grill them as much as you want. Okay, so I hand over to them.
Good morning, everyone. Till now, we have covered Euler-Bernoulli beam theory, Timoshenko beam theory, and the rod theory, special Cosseret rod theory for solving elasticity problems. And based on the previous knowledge, we are looking at a few examples of rods specifically. I mean, how do they behave actually? So, the very first example is cantilever beam that has been covered for each of the cases in the class. The boundary conditions are same as we have discussed. At the clamped end, there would be no movement, so rotation and displacements are 0. And at the free end, there is no moment, and a static load is acting at this free end, or constant load is acting at the free end. I think we have solved the analytical solutions for Euler and Timoshenko beam theory for this case. So, based on those solutions, I have some plots here. The very first one is load versus tip deflection for each of the cases. Now, as we can see that for lower loads, all these theories, they agree with each other. But at higher loads, the Timoshenko and Euler beam theories, they don't, they're no more reliable actually. As we know that the rod theory incorporates large deflections, large rotations and everything. So, and Timoshenko and Euler beam theory actually hold for the linear regime only. So, they agree only for smaller loads, but at higher loads they deflect from the actual path. So, this is all about load versus tip deflection. So, any doubts or? So, and next is this. In case of rod theory only, this is axial position versus tip deflection. This plot we get when we increase the load like this. The load is being increased from right to left, and we can see that I have taken length of rod equal to 5, and we can see that as the load increases, there is axial displacement also, and the rod gets shorter and shorter with the tip deflection increasing from 0 to 3.
Rod does not get shorter, right?
Sorry,
it just displaces.
Yeah, it displaces, or we can say, that it will look shorter. It's not the material.
But also when transverse deflection.
Yes, with the tip deflection. Initially it is like this, and then it will displace and look like
It's going to be like shorter.
it's okay. So whatever, it's simple like this. So this kind of behavior we don't see in Timoshenko and Euler-Bernoulli beam theories, only for rod theory. And anything else? Okay. And then this is that error analysis that we already covered in the class. I will write down the formula before discussing this actually. This was displacement for Timoshenko and Euler-Bernoulli divided by this, and it was, I think, 1/4 E by kappa G and H by L square. Right, this we had done already in the class, this error analysis. Now for error to be really small, we will put this value less than 1, so it will give me L by H is much greater than 1 by 4 E by kappa G. So for different values of, here are our material properties and these are the geometric properties of the rod. So based on this little formula, we can find out how much is the error if we change the geometry of the rod. So it comes out that for slender and long beams, for L by H equal to, this is the plot for L by H equal to 20, means a very long rod or a perfectly slender rod. The Timoshenko and Euler beam theories, they coincide with each other. But for shorter beams, that means for L by H equal to 5, the Euler-Bernoulli theory does not coincide with Timoshenko, so that's no more reliable now. So basically for shorter beams we should go for Timoshenko beam theory, and for longer beams we can use Euler-Bernoulli beam theory. So this was what where to use Euler-Bernoulli beam theory and where to use Timoshenko based on the geometry of the rod. We can easily find out that using that little formula.
You can also say that the shorter or longer is a relative term and it is related to that right hand side over there. Can you put it up? It's possible that there is a scenario where L by H equal to 5, but the right hand side is, let's say, 0.1, it's square root of 1 by 4. So it tells again both the theories will give the same result. So 5 need not be always small. It has to be related to that term on the right hand side. So even for L by H equal to 5, both theories could give same result.
Yeah.
If the right hand side, for example, is let's say 0.1, right? So 5 is much more greater than 0.1, so which means both will give same result.
A question. The choice of Euler or Timoshenko, does it depend on the cross section of the beam? Because you explained now with the rectangular cross section. Is it all same for circular or I section, something like that?
Yeah, it goes for that, because this one was for rectangular cross section, but when we derived it, it was in terms of area, not H and B. Then we, area and moment of inertia actually I. So we can use that instead of this.
So it again depends on this ratio only.
No, so the constants will come out to be different. Because the area, for example, over there is not H square. If circular, then it is pi times H by 2 whole square, right?
Yeah.
If H is the diameter. And similarly, I is not 1 by 12 H to the power 4, it is something else for circular. So you plug in those values there. And finally, it will look like pretty much this, but with a different constant on the right hand side.
It would be L and D rather than NLH. Maybe.
Yeah. And the constant that you see there, 1 by 4, could be something else, depending on the cross section.
Timoshenko works always for all of the cases. So what's the advantage of the Euler-Bernoulli?
What's the advantage of?
Yeah.
Of what?
Euler-Bernoulli.
Oh, of Euler-Bernoulli.
Yes.
Because it is simpler. It is very simple. Euler-Bernoulli theory is the simplest theory that people started with, and it works if L by H is much greater than that ratio. So people like to use simple theories. For many people, Timoshenko is still very complicated. Maybe you don't feel it is complicated, but there are many people who feel like Timoshenko theory is very complicated. Why go for Timoshenko? Why don't we just use other Bernoulli? So for them, this is perfect, right?
For analytical solution, it's difficult for the main translation has also.
And both analytical and even understanding the theory. It's very difficult to understand shear for people. But bending is fine. But when you introduce shear, they start thinking what's going on. So for them, Timoshenko becomes difficult.
Yeah.
But we are in mechanics community. For mechanics community, I think both are equally good, isn't it? Yes.
So we have two factors of influence to the sensitivity of the length. We have,
Yes.
on the one hand side, we have the ratio between Young's modulus and shear modulus.
Yes.
And on the other side, we have this geometric influence.
Yes.
And is there any rule what makes it more sensitive? Is it the ratio between the moments of inertia in the two main directions?
No, that does not come here because this is for planar deflection. So we have to first think of which plane the beam is deflecting in.
Okay.
And then we only take the moment of area of that particular plane.
So sorry, I meant the moment of area.
Yes.
The ratio between
Yes.
them. That is
No, again, we don't take the ratio of the moment of area.
okay.
So what will come here would be the ratio of area of the cross section and the moment of area about the axis in which it is deflecting.
Okay.
Yes. So the other moment of area will not come in the
Yeah.
picture.
Okay.
Only if you are deflecting in, let's say, the other plane, then that moment of area will come in the picture
Yeah.
with the area of the cross section.
Okay.
Yeah.
Okay.
So asymmetry of the cross section, I think that's what you're referring to, whether if the two moment of areas are different,
Yeah.
does that somehow affect this analysis? So that does not affect if you are restricting to one particular plane,
Okay.
then the other ratio, the other moment of area does not come in the picture.
Okay.
Yeah.
Only this factor kappa, which is actually coming from the shear sensitivity.
So 1/4 will be, that constant will change.
Yeah. Okay.
So if you take,
And this is due to the shape of the cross section.
yeah, this is dual shape. So 1/4 is somehow also, it's different for different shapes.
Yeah.
So
Okay.
that's going to change.
Okay. So actually, the factor of influence is 1/4 kappa,
Yeah,
which
right.
changes
Okay, yeah.
due to the shape of the
Yeah,
cross section.
or about,
Mm.
or which will change if you change the axis of,
Yeah.
or the plane of the deflection of the beam.
Okay. Thank you.
Next one is follower load problem. We have also discussed the boundary condition of this particular case. It's similar to cantilever, just that the load acting at the other end is always perpendicular to the center line. So instead of PE1 we have PD1 here. The directors instead of the E1, E2, E3 coordinate system. So this kind of plot we get after, how the rod deflects when we apply the load or follower load. We can show the animation also for the follower load problem. I think that's it. This is how it deflects under
As the load
that,
is
as,
increases.
yeah, as the load increases actually. Should I write it once more? That's it. So, yeah. And then he will take over.
So now we will be discussing about the buckling of rods, and this is the compressed state of our rod. So it is compressed in such a way that if you look towards the ends are clamped towards the transverse displacement and the rotation. So there is no rotation allowed at the ends of the cross section, and only the axial displacement is allowed. So can you think of the boundary conditions for that? Okay, where is one? So let us write the boundary condition at s equal to -1. So what are my little r and capital R? Can you think of what is capital R? As I said, there is no rotation allowed. Identity, exactly. So R is identity at -1. Okay. So now let's see, is there any transverse displacement allowed? No. So R, what's the first component of R in the even direction? Is it allowed to go up? Then 0, exactly. And what about R2? It's same, 0. Now what's about R3? You assume it that the length of the rod from 0 to -1 is L. Let's assume it, and so its total length is 2L. So can you say now what is R3 at -1? So you see, as the rod is compressed, the length decreases. Yeah. So this would be, it decreases by lambda times L. So this is 1 plus lambda times L. So that would be a boundary condition for this. Now similarly, if you do for
lambda is the compression. So lambda is like the.
It's a compression, yeah. It's an action
Ratio.
displacement. It's a ratio, yeah. And then similarly for s equal to 1, R would be identity, capital R would be identity, R1 and R2 would be 0, but R3 would be so with those boundary conditions,
That should be 1 plus lambda or 1 minus.
minus
Lambda
because
is-
length is decreasing. So with that configuration, we compressed our rod and we found that it buckles in a Euler buckling mode. Okay, so as I compress a rod, it buckles and gives me the Euler buckling configuration. So if I look towards the buckling load of this kind of rod, I would find that as the L by D ratio increases, so this is my buckling load which I have normalized with the Euler buckling load 4 pi square E by L square, and as the L by D ratio increases, my rod behaves like a Kirchhoff rod, but for for less L by D ratio, because of shearing and extensibility effect, the load, buckling load decreases. So that's why we see that there is a gap here.
What's a Kirchhoff rod? Can you just
So Kirchhoff rod is like a Euler rod. I mean, where it's a rod in which is unshearable and inextensible.
in terms of the strains, maybe you can talk about it. In terms of V.
V3. So yeah, okay. So when I say V, so for the unshearable, inextensibility means 1. Inextensibility means 1, but unshearability can't be counted here. I mean V1, that comes out from the constitutive law, the constraint which we need to apply for that.
V1, V2 or 0 basically.
So
So
unshearable.
for a special Cost-Rat rod, we have arbitrary V. So V is a strain measure, right? We have found out. But the Kirchhoff rod is a special kind of rod which neither shears nor stretches. So that would mean V1 is equal to 0, V2 equal to 0, and V3 is equal to 1 always.
So as this rod cannot deform in any way, it's just a simple model for buckling then?
Yes, yeah, so it can buckle and twist, sorry, it can bend and twist.
It can bend.
K is there,
Okay,
but V is not there.
okay.
So Kirchhoff rod is such a rod which only undergoes bending and twisting. There is no shearing and stretching. And for such rods, Kirchhoff rods, one can find out the analytical formula for the buckling load, which is 4 pi square EI by L square. So if you compress a Kirchhoff rod, the analytical formula for the buckling load can be derived, which is 4 pi square EI by L square. But we were working with special Cost-Rat rods in which a rod can shear as well as stretch. So because of those extra effects, the buckling load is not really equal to 4 pi square EI by L square, it deviates from that formula. So therefore you see that the red line does not match with the blue line. But it turns out when L by D is very large, the two theories give the same buckling load. But when L by D is small, the two theories give different buckling loads. So it is also proved that if L by D is very large, then the effect of shear and stretch is negligible. And therefore Kirchhoff theory works. The theory of Kirchhoff rods work. But if L by D is small, then the effect of shear and stretch are not negligible. You have to also take them into account, and that's where the application of special Cost-Rat rods becomes important.
So if L goes to 0, it would be the buckling load.
Yeah, and that's not even the regime of the beams, isn't it? If L by D, for example, becomes 1, you are talking about 3D structure now. You cannot model them using beams.
Those equations, what did they give?
Yeah. Do you remember?
No, I don't remember. I think, yeah. We can try it. Next we see the buckling in the twisted rod. So if I twisted my rod and then try to compress it, then the configuration which I'll get is this. Now the buckled solution is no more planar. So earlier it was a planar solution, that's the Euler buckling mode. But now you will get an out of plane solution for that.
Yeah, so this is really interesting. We are always familiar with buckling. As you compress a beam, then it buckles something like this, isn't it? And the buckled solution is planar. But if you twist a beam and then compress, then the buccal solution is no more planar. It takes a 3D shape, it takes a loop-like shape. That's what you see over there. So that's the effect of twist. If you have twist in it and then you are compressing, then the buccal solution is no more planar and it takes a shape like this.
Is that really buckling? You twist and then you simply relax.
Yes.
In actual direction, it would immediately
Not
reduce
immediately.
its shape.
You have to compress it to some, you have to reach a critical compression.
Okay.
Yeah. But he will have a slide where what you are saying can also come.
So if I look towards the buckling load, which I again normalize with the Kirchhoff load, so I'll find that you see that in this plot, it does not start with 1.
So your axis is twist, right?
Yeah. So I'm plotting my buckling load with respect to the twist, and at 0 twist, you see that for a particular L by D, so it does not behave a Kirchhoff rod because the extensibility and shear stretch is being accounted in the specific Coursera rod formulation. So as I increase the twist, I find that even at 0 load, the twisted rod buckles. So if I increase my twist, I'll find that the rod buckles even at 0 load. And in fact, the buckling load gets negative. That means I need a tensile load for that for buckling. If the twist increases, it's in such a manner that a stretch is required for that buckle.
So I hope you got the masses here. It's very interesting. You know, we always have this intuition that if you want to buckle, you have to compress the beam, isn't it? But what this tells us is that if you have twist in it and then you want to buckle, you require less compression. You see the buckling load is reducing. So you require less and less compression if you already have twist in the rod and then you are compressing. And actually if you have a lot of twist in it, then it can buckle even without compression. And in fact, it requires you to stretch a beam if you don't want it to buckle. So that's why it is showing that if you have a lot of twist, then the buckling load has become tensile, it's negative. So which means if you don't apply any force, it will automatically buckle. If you want to stop buckling, you have to apply some stretch. Then only it won't buckle.
So in the class we have studied the strain energy per unit undeformed length for a rod, and we have written the formula till this part, A, B, C and D. E was not accounted. So
What is E?
E is actually the extension and twist coupling. So once I put this strain energy in my formulation, and then I compress my rod, I'll find that it again not buckles in a planar solution. It gives an outer plane solution, and it is due to the fact of extension and twist coupling. So what happens is when I'm compressing, the fibers of the rod start twisting due to this coupling. So I do not see a planar solution for that. That's why I see a out of plane solution for that.
Can you give some explanation why E comes here? What's the origin of this coupling E? Coupling between extension and twist.
So if the fibers are, for example, of a rod are straight fibers.
Yes.
So then in that case there is no effect of, it's just if you stretch it, the fiber will stretch. If you compress it, it will compress. But if the fibers of the rod are in chiral form or the helix form, so once I compress it, so the fibers will start twisting as well. because of this because of the nature that in that chiral rod the extension and twist coupling is non-zero.
There are many applications also in nature. For example, you must have seen the picture of DNA. You know, it has that helix-like thing. So, if you want to think of it as a continuum beam and want to incorporate the helicity of these strands, then you have to think of it as a pre-twisted beam. A beam which is already twisted, but there is no moment in it. So it has intrinsic twist in it. Which means although the beam has got twist in it, but there is no twisting moment in it. So it is naturally having that twist. And for such beams, the energy form has an extra term that 2E times U3 minus 1 into K3. So you see, because it has this intrinsic twist in it, if you try to stretch such beams, it will also automatically twist. You know, if you have an isotropic beam, for example, you stretch it, it never twists. It never twists. But if you have intrinsically twisted beams, if you stretch it, it's also going to twist. So that's a very interesting effect. And to model that effect, that extra term is introduced, which models the coupling between extensor and twist. And if you put that in your rod equations and solve for buckling, the buckled solution turns out to be like this. So again, it is no more planar. The buckled solutions are non-planar. And that's what is found even with DNA. If you buckle it, if you compress a DNA, the buckled solution takes such a shape. So you can model the buckling of a DNA by having that extra term over there, extension twist coupling term. Yes.
How is this factor derived?
Which factor?
This is the factor E.
Yeah, so that's again we'll talk about that, how to get those constants A, B, C, D. So A, B, C, D we already found out from comparing with simple beam theory. But for capital E, one has to again derive it from 3D elasticity. And there is a very simple formula for that, I don't really remember. So basically this capital E is proportional to the intrinsic twist. Whatever is the intrinsic twist in the beam, capital E is proportional to that. And there's an extra, there is some more terms there, I don't really remember. Yeah. But maybe I'll show you in the next class what is that.
Thank you.
This presentation will be shared. Sorry? This presentation will be shared for us.
Yes, of course. So it will be there on that drive.
So that's E.
The coupling constant E. What is that theta?
So theta is the small twist.
That's the intrinsic
Intrinsic twist.
Let's explain this term.
So this formula holds for only thin circular tubes made up of orthotropic material, and here E1 is actually the Young's modulus along the principal direction which the twist about. With G12 is the shear modulus and mu21 is the Poisson's ratio. J is your polar moment of inertia.
Area.
Area, yeah.
So as you can see in this formula, if the beam is isotropic, the thing inside the bracket will be 0, right? Because Young's modulus is 2G times 1 plus mu. So for an isotropic beam, this constant is 0. But if the beam is not isotropic, if it is orthotropic, and it has intrinsic twist also, like theta that you see over there. So then this constant is non-zero, and you have that interesting effect of extrinsic twist coupling there. You have that paper with you? You have it with you?
Yeah, this was my.
E perpendicular or E1? E1.
E1.
Okay.
So that's the Young's modulus in the direction of the fibers which are pre-twisted. Okay, so in the last class we had worked out the equations of elastic rod, wrote it as a system of first order ODEs, system of 13 coupled non-linear ODEs. We wrote down the boundary conditions and we said how to solve them. And we had a very simple example of the strain energy function phi of v comma k, which was half of a times k1 square plus k2 square. Again, this was scripted, plus half of b times k3 square plus half of c times v1 square plus v2 square plus half of d, scripted d, times v3 minus 1 square. So we wrote down this function, but without really thinking much, we just wrote it down. If you ask how this came up, then we don't have any answer to that as of now. How did we come to this formula? Isn't it? So we want to do this more rigorously. How to obtain the formula for phi? Just few moments ago you also saw it could have a coupling term. So when those coupling terms arise, can it have some extra terms also? So how do we know when will that come, when will that not come? So that's what we want to figure out now. Okay, so we all have learned in 3D elasticity the concept of material symmetry. Material symmetry. Yes?
I don't find much difference, but last time you wrote the K for C and C for K.
Yeah, don't worry. I think, I must have mixed up those constants. Yeah. Okay, so all of us know about the concept of material symmetry. We start with W, the 3D strain energy density, being the function of deformation gradient big F. Then we apply objectivity or frame indifference, and we say that the energy function should only depend on the U part of the polar decomposition of big F. And if you use further symmetry, the 3D material symmetry, for example, if you use isotropy is a example of material symmetry. So if you use isotropy, then it turns out that the energy function depends on those three invariants, right? I1, I2, I3. So they are strain invariants. So it gives us a lot of idea about how would the energy function look like. Because this is an unknown function and we want to get as much as possible from theory and then maybe proceed for experiment. So isotropy tells us that the energy would only depend on these three invariants, and if it is let's say orthotropic, you get some more invariance. So we want to do similar thing for the case of elastic rods. We want to apply material symmetry and understand more about how does this energy function look like. Okay? So that's the topic today. Maybe I'll write here. Material symmetry in elastic rods. Material symmetry in elastic rods. Okay, so the idea is, let us suppose we have our beam here or the rod in the reference state and I deform the beam or the rod through some deformation map, and the rod, maybe it undergoes this deformation, and in the next, so this is first, you can call it as a theoretical experiment. In the second theoretical experiment, suppose I rotate this beam about the E3 axis. Okay, that's the E3 axis. So this is rotation about E3 axis. And then I apply the same deformation, f, little f. Okay, and then we want to understand how do the energies of the rods in these two experiments finally, are they comparable, are they same, or they are indifferent, or they are different. So what do we do in 3D elasticity? In 3D elasticity, we first apply some deformation and then think of the energy of the deformed body. And in the second experiment, we first apply some rotation and then apply the same deformation as we have done here, and again think of the energy in the deformed body. And if the pre-rotation that's being done here, if it is in the symmetry group of the material, then it turns out that the two energies here are the same, isn't it? So if the rotation, if this rotation about E3 axis lies in the symmetry group, then the final energy in the two theoretical experiment would be the same. So I am just giving a very brief recap of symmetry. It's a topic on its own. It's not so easy, but I am assuming that you all know about it. Okay? You remember what you did in case of frame indifference? In case of frame indifference, our first experiment was we applied some deformation. In the second experiment, we apply the same deformation and then rotate. But here we first apply rotation and then deformation. So the experiment in frame indifference, rotation comes later on, but for symmetry operation, rotation comes first and then we apply deformation. Okay, just a brief recap of symmetry idea. Now we want to do the same thing for our elastic rods, and we want these rotations to lie in the symmetry group of elastic rods. Suppose that we have a circular rod to begin with. Okay, think of a circular rod, and if I rotate it about E3 axis, does it look the same? Does it change? Or it would look the same, right? If it is circular rod, you rotate about E3 axis, you won't be able to distinguish it. So therefore, the rotation about E3 axis lies in the symmetry group of such rods. What symmetry group? So symmetry group comprises of all operations which, when you perform, leads you to the same body, isn't it? So here you have an elastic rod, circular. If you rotate about E3 axis, it still looks the same, right? So you see, in 3D elasticity, the symmetry group does not depend on geometry, because there we talk about local symmetry of the body, but here the symmetry also depends on the geometry of the rod as well as on the material of the rod. You know, for example, if your material is, let's say, orthotropic, if it's an orthotropic material whose one principal axis is in E1 direction and other is in E2 direction, and you rotate by, let's say, 10 degree, then the principal axis are not coinciding with what it was earlier. So it's not the same rod now. So that's not in the symmetry group anymore. So in case of rods, when we talk about symmetry group, we have to take care of both the local material symmetry as well as the symmetry from the point of view of geometry. Okay? So suppose, and one example would be if you have an isotropic circular rod, then certainly you do any rotation about E3 axis, it's going to lie in the symmetry group, isn't it? Okay, so now for the theory purpose, let us just say I am applying a rotation Q here, which lies in the symmetry group. So I don't want to talk about what kind of beam this is, but let's just say that the rotation is such that it lies in the symmetry group of the beam or of the rod. And then I apply the same deformation, then the two energies should be same, isn't it? That's what the concept of symmetry is. But we know that in case of rods, the energy actually depends on V and K. So we like to find out what's V and K in the first case and what's V and K in the second case. So suppose in the first case, when you apply that deformation map little f, the rod deforms in such a way that it generates little r comma capital R in the rod, and the strains are further V and K, okay? And we would like to find out what's the new V and K here in terms of the old V and K. Alright? So in the first experiment, the deformation maps were such that it leads to small r and big R. But in the second experiment, what will be the new small r? Can you think about it? What will be the new small r, r new of S? So see, what we have done is we have just rotated the beam. Although I wrote it down here, it's actually over there only. It's just rotated about E3 axis, and then we apply the same deformation map. So what will be the new small r? Same as the old small r, right? Because we are applying the same deformation map. So because the beam remains at the same location, although it's written here for clarity, but you rotate about E3 axis, it remains over there. So any cross section will go at the previous location because we apply the same deformation. So r little r new is same as old r. What about the rotation? What about the new rotation? How is that related to the old rotation? You see, you first applied Q and then you are applying the same deformation. And the deformation was such that it was generating capital R. But here you already had the Q earlier, and then you are applying on top of it the same deformation map. So what will be the new rotation? QR? So it's going to be RQ. So big R times Q. So you can always remember, when you have series of rotations, what comes in the rightmost is the one you apply first, and as you go to the left, you apply those rotations successively. So you first apply Q, then apply R. Therefore, it is big R times Q. When we were doing frame indifference, the new rotation was big Q times R, because there you had applied rotation after the deformation. Okay, so this is big R times Q. So let's find out what is new little v and what is new little k. So because of this, what's v new? V new is simply going to be rotation new transpose times little r new prime, which is same as big R new is big R times Q, take its transpose, so it becomes big Q transpose times big R transpose times little r new prime, but little r new is same as old r, so it is same as little r prime. But big R transpose times little r prime is your old V. So V new is equal to Q transpose times V old. Right? Then we talk about new K. What is K new? So K new is then again the axial of big R nu transpose into big R nu prime, right? R transpose R prime, that's K. Now we write down new big R in terms of old big R, and that's going to become axial of Q transpose big R transpose big R prime into Q. See, there is no derivative on Q because Q is a constant. So you are applying same rotation everywhere. Q does not depend on S. Okay? And what could you write this as? So axial of this would be same as Q transpose times axial of big R transpose big R prime. No, we had done this earlier in the class also, when we had that objectivity. And this is then same as Q transpose times K, the old K. Any question till now? So we have found out what is new V and new K in terms of old V and old K. And then we apply symmetry. Since the Q, this rotation Q, is in the symmetry group, so what can we say about energy in the two cases? They have to be the same. So what this tells us is that phi of V nu comma K nu is equal to, oh, we had psi, not phi, isn't it? For energy we were using psi. So phi? Yeah, I think we were using psi. So we'll use psi. Okay, so psi of V nu K nu would be same as psi of V old K old, which means psi of Q transpose times V comma Q transpose times K is equal to psi of V comma K for all Q in the symmetry group. You know, we could write it as some symmetry group G. And now we want to exploit this. We want to exploit this formula and obtain more information about how this energy function will look like. Okay? So any idea what can we do now? So you have to think about what do we do in 3D elasticity. We find out the strain invariance. With isotropy, for example, we get I1, I2, I3, the three invariants. So here also our goal would be to obtain invariance, the quantities which are invariant under these operations. Okay, so let's think of an example. So now we have to talk about specific rods or specific symmetry group. So think of the symmetry group that G equal to SO2 all rotations about E3 axis. Rotations about E3 axis, and certainly rods which are circular and isotropic will have this symmetry group, and there are many other rods which will also have this symmetry group. If you think of a rod which is intrinsically twisted, for example, a cable or a rope which is pre-twisted, they also have the symmetry group, isn't it? Their symmetry group will also be SO2. So you think of that rope, you rotate about its axis, still looks the same, isn't it? Of course, the rope has to, or that rope I can draw a picture here. Maybe so that's the helicity in the rope. But that has to be lot of them, it has to be infinite. There has to be infinite number of fibers so that there is continuity of those helix. If there are only, if you have a rope which you form by intertwining two ropes, you take two ropes and then intertwine them, then there are only two helix. And can you think of what's the symmetry of such ropes? If you rotate about E3 axis, what all rotations will lead to the same rope? Only finite rotations, right? So what will they be? Only the discrete rotations, and it's called, I think, twofold symmetry, isn't it? Twofold symmetry. It has got some special symbol, isn't it? Do we use D or N? Anyway, forget about it. So it's a twofold symmetry. So you can only do 180-degree rotations, it leads to the same rope. If you have three such ropes intertwined, it has threefold symmetry. If you have four such ropes, it has fourfold symmetry. And if you have infinite such ropes intertwined, then that discrete symmetry will become continuous symmetry, and it will have that SO2, all rotations about E3 axis. So you can think of a continuum beam which has infinite such ropes, and then it has SO2 symmetry, isn't it? So let's think of what invariance do we get when the rod has SO2 symmetry. It has continuous symmetry about E3 axis. So what all rotations are present there? So in such cases, what will be Q equal to? That's 0, 0, 1, 0, 0, cos theta minus sin theta, cos theta, right? And then this is for all theta in 0 to 2 pi. So that's your SO2. Now we think about if this is that rotation, what happens? What does Q transpose V become? Think of applying this rotation to V. look over there, Q transpose V, Q transpose K. So V nu, which is Q transpose V. So write down the whole thing. That Q into V1, V2, V3. What does this become? Can we say that this is same as cos theta minus sin theta cos theta into V1, V2 and V3, isn't it? Yes, with the transpose. So this becomes sin theta minus sin theta. Okay. Right? So what you see is that under this operation, V3 does not change. And V1, V2, they have sort of rotated. So if you think of V1, V2 as a vector, so you know, this whole thing was together as a vector, but take a projection of it, just the E1, E2 part of this vector, V1, V2, and call it as V tilde or V hat. So say V hat is equal to V1, V2. Then V nu is equal to the rotation Q on V hat and V3. Isn't it? Similarly, for K nu, okay, with this the transpose is equal to Q transpose times K hat, where K hat has got only K1, K2 and a K3. Okay?
Then we should also put a hat on the Q.
Yeah, we can also put hats on the Q because they are just 2D projections. Q hat transpose, Q hat transpose. Okay, now we want to find out the invariance. Can you think of what will be the invariance? I mean, two of them you can already see here. What did not change? Yes? V3, K3, right? So V3, K3 did not change, so they are definitely the invariants. Can you think of other quantities which did not change? And you have to think of all the rotations, all SO2 rotations. Now think of this V hat. So think of this vector V hat. And the other vector K hat. Whenever we apply this Q hat, because both of them are rotating by the same quantity, so they are going to rigidly rotate, right? The angle between them will be preserved and their own magnitude will also be preserved. When you do such rotations, the angle between them will be preserved and the magnitude of each of them will also be preserved. So what are the invariants? Magnitude of V hat, for example, right? Isn't that an invariant? That does not change. What's the magnitude of V hat?
Scalar product between those two is a invariant.
that's also invariant. The dot product is also invariant. So the angle does not change. So therefore the dot product is also invariant. The cross product is also invariant. So it turns out the invariants, all such invariants are, one is the magnitude of v hat, then magnitude of k hat, then the dot product between v hat and k hat, and the cross product v hat cross k hat dot E3. So these are invariants, and of course V3 and K3 also. And you could further write it down. So this is, for example, V1 square plus V2 square. This is K1 square plus K2 square. This is V1 K1 plus V2 K2, and this would be V1 K2 minus V2 K1, then V3 comma K3. So these are all the invariants if your symmetry group is SO2. Okay? So what this tells us is that your energy function psi then actually depends on those invariants. So it should be a function of V1 square plus V2 square, one invariant here, then K1 square plus K2 square, then V1 K1 plus V2 K2, then V1 K2 minus V2 K1, then V3 K3. Okay, so you got a lot of information. Okay. What more can we do? See, these invariants were for SO2 symmetry. What if you also include reflection in that symmetry group? Reflection in the E1, E2 plane. So again, think of your twisted ropes. It has got that helix, isn't it? If you reflect that twisted rope about E1, E2 plane, can you think of what's going to happen to that rope? Will it look the same as earlier? So you have the twisted rope, you reflect about E1, E2 plane. Here is the twisted rope. This is the E1, E2 plane. You reflect about E1, E2 plane. So what happens due to reflection? You know, E1, for example, will become minus E1. E3 will become minus E3. E2 remains the same. So in this plane, so you have a mirror and you look at the mirror image. So, you know, one of the things that would happen is the helix that you have, if it is turning clockwise, and when you apply the reflection, it will become anti-clockwise. So the handedness of the helix will change. Can you see it? Just look at the rope and think of reflecting in the E1, E2 plane. The handedness of the helix changes. No? So you get a different rope. So of course, that reflection cannot be in the symmetry group for a pre-twisted rope. But if you have a rope which is not pre-twisted, for example an isotropic rod, the reflection will also be in the symmetry group, isn't it? The reflections will also be in the symmetry group. So now can you think of what happens to the invariance if you also include reflection here? What happens to the invariance?
The one with that comes from the cross product, we change the sign.
The one which comes with the cross product.
V1 K2 minus V2 K1 is basically K1 V2 minus V1 K2.
Yeah, that's true. Yeah, that's going to happen. Anything else? Yeah, what about V3 and K3? V3 will change to minus V3, K3 will change to minus K3. And of course, the cross product changes. What about the magnitude? Magnitude won't change. This one change, this one change. Dot product, that's also not going to change. The angle cos theta will be the same. This is going to become negative. That's also going to become negative. K3 becomes negative of K3. So you have, what happens to the invariance? You have to take the square of them. So the square of them are the invariant. So K3 square would be an invariant. Instead of K3 square, because K3 square is not changing now. Similarly, instead of this, you will have a square of it if you include reflections also. Okay, so that was just a side remark. Let's just work with proper rotations. So these are the invariants, and that's how your energy functions should look like. So once we have this, what more can we do if you want to get the expression of the energy? What should we do then? So call this I1, call this I2, call this I3, call this I4, call this I5, and call this I6. You have 6 invariants. Okay? How do we get the expression now? The expression for energy. Once we have the invariance, what should we do? And we are pretty much stuck here then. If you, for example, want to get the polynomial form of the energy, then you can do some Taylor's expansion. But if you are not happy with polynomial form, then you have to do experiment. So after this, you have to go to experiment. But if you want to get, let's say, polynomial form of energy, then you can do Taylor series expansion. So psi, for example, is a function of V1, V2, V3, K1, K2, K3. So you can, so V1, V2, V3, K1, K2, K3, or V comma K. So you can do its Taylor expansion about some reference strain, and then this would be psi of V naught comma K naught, which is the reference strain, which could be your stress-free reference state, for which V naught is going to be 0, 0, 1, and K naught will be equal to 0, 0, 0. So that's a straight state. The strains in the straight state where V1, V2 is 0, V3 is equal to 1, K1, K2, K3 are all 0, straight rod. And then you can write this plus del psi over del V at V0 comma K0 dot V minus V0 plus del psi over del K at V0 comma K0 dot K minus K0 plus the quadratic term half of del 2 psi over del V at the reference state times V minus V0, and then you take another dot. So once you have done this, dot with V minus V0. So this is a matrix. Matrix times this vector, you get a vector, and dot with that vector, it becomes a scalar. Similarly, for del 2 psi over del k into K minus K0, and this thing has to be dotted with K minus K0. And then the cross term plus del 2 psi, twice of del 2 psi over del V del K into K minus K0 dot with V minus V0. This is the Taylor's extension for multivariables. And plus, of course, the higher order term. Okay? Because often we want to work with polynomial expression for energy. So this is what we do. And then what are the unknowns here? The coefficient. This is an unknown. This is the coefficient unknown. This is an unknown. Del 2 psi over del V2 is an unknown. How to get those unknowns now? No, this is the constant term. You can forget about it because in energy constant terms do not matter. So you just forget about it. This is the first derivative, del psi over del V. What is del psi over del V? Do you remember? That's the force, right? In the director frame. And if your V0 and K0 are the strains corresponding to straight state, what will be del psi over del V there? What is the force in the straight state of the beam? If the beam is not deformed, what's the force in it? It's 0. So that's also gone. If you are expanding about V0 equal to 0, 0, 1 and K0 equals 0, 0, 0. So we have to now get these constants, del 2 psi over del V, del 2 psi over del K, and del 2 psi over del V del K. How do we get them? So if let's say I want to get del 2 psi over del V, this is equal to del over del V of del psi over del V. This is not really easy, but that's what we have to do. This is same as an del over del V of del psi over del V. But psi's, they depend on those invariants. So you have to apply chain rule and write as del psi over del I1 into del I1 over del V plus del psi over del I2 into del I2 over del V plus you keep on doing it and then take another derivative and you see del I1 over del V. This is something you can obtain because I1 is V1 square plus V2 square So you have the formula for I1 in terms of V. So del I1 over del V you can obtain. But del psi over del I1 is now an unknown. Because we don't know how does the psi in terms of invariance look like. So this you can compute. Can compute. But this is unknown. This also can compute, but this is unknown. And you see you have to take another derivative. So same thing you do for this one and for del 2 psi over del V del K. Once you have done all of them, then you start collecting the coefficient of, for example, this V minus V naught dot V minus V naught. It's a big business, but just some algebra. Something that you can do. You don't have to think, just keep on working. And once you do that, then you have obtained what you wanted to. The quadratic form of energy, psi, that will come out to be half of A times scripted A times V1 square plus V2 square plus B times this is K1 square plus K2 square B times K3 square plus C times V1 square plus V2 square plus D times V3 minus 1 whole square plus 2E into V3 minus 1 into K3 plus 2F into V1 K1 plus V2 K2. So this is a definite way to derive this as well. You don't have to do any hand waving. You derive it rigorously and get to this quadratic expression for rods which have SO2 symmetry. And of course, the constants here A, B, C, D, E, F, these are something you cannot determine from theory. You have to do that experiment. And you see this coupling term automatically comes here. There's another interesting coupling term, coupling between bending and shear. Okay, so more about this we'll talk in the next class.
Maybe just one announcement. For those of you who want to take the exam, we will pass around a registration sheet here where you can just enter your name next week when we meet next Tuesday. And then you can register for the exam.